Today's lecture is going to be an introduction, and since there is nobody is in the room I'm acquainted with, I have no idea about your background. Mostly it concerns algebraic geometry. So, first of all, please interrupt me if I'm using some words you'd like to be explained. And from time to time, I'll ask you whether it is clear what I'm saying. So, today's lecture is the introduction, as I said, so we'll call it like this: arithmetic geometry. As you see, the title concerns a more wide domain than this course in general. I mean, for some time we'll speak about arithmetic varieties of any dimensions, but some explanations are really needed. So I would call it just a glimpse. Для русских общий взгляд, наверное. Well, what we start with the subtitle of it in a more classical form. We are going to discuss indefinite definite equations. All our equations are going to be algebraic, so perhaps I'll never mention it explicitly during the whole course. Now let's start with what everybody knows from the high school. So I write it just the quadratic equation. I'm writing down the quadratic equation. Not that I'm going to tell you something about them that you don't know already. However, perhaps there will be some question about which I'm not really sure. But for some time we'll operate with it or discuss it purely algebraically. I mean, not specifying the meaning of the three letters that participate here. Perhaps you understand, we all of us are trained in the school in such a way that we understand that the role of these three letters are different. Two of them are called coefficients. One of them is called unknown. So it is an equation in X. However, for some time I'd like to forget about it and draw the surface, the arithmetic surface, defined by this equation, and then discuss some terminology related to our course. So, although I do not write down anything explicitly, drawing these objects on the blackboard literally means that we are discussing the real picture. So the professional notation for it is /real, though perhaps I should emphasize that in the theory of quadratic equations there is not much effect of the both coefficients and the unknown to be real. So, well, I have a computer drawing of this surface. Unfortunately, it does not really help me. I don't know, maybe you see it immediately. In fact, I'm not good at drawing space pictures, but this time what we really know, that there is a special curve on the base of it, minus q is 0, so we have to try to show this q is so in the horizontal plane we have something like a parabola. Please believe me that it lies in the horizontal, in the PQ plane. And here it is, the parabola. So the x exists whenever this number, q is p squared over 4, so it is like this. And what I really know, that the surface is called the paraboloid. I'm not really sure how do I draw it. Well, perhaps I don't torture myself. It is some abstract surface. Maybe you see in this way I'm not prepared at all. So I just write symbolically that over the plane PQ there are pieces, and generally we are interested in, generally the projection is 2 to 1. Now, in order to write it in a clearer fashion, so you see I failed to draw anything clearly. Then we do a very important thing. We give name to this equation, and we are going to do it always. So my suggestion is the name. It is a quadratic labeled PQ. So it is a surface, and what we try to draw here is like this, the quadratic. Now I'm saying something maybe a bit new. The main hero of today's lecture and maybe of the whole course will be the argument like this. Well, let's decide here that P and Q are real, though, as I said, it is not really important for the tricks we are doing. So this is the name of the surface. And solving equation geometrically means just that over the plane with the coordinates PQ, we are finding two equations. And we say that it is, well, perhaps I denote it like pi, and what we know is that the inverse of the point PQ, or rather its cardinality, is 2 or 0. As for 1, I'm not sure, because we better count the multiple roots in such a way that over this discriminant curve we have just 1 point taken once. Все, теперь можно...
Все нормально теперь.
Ага, можно посмотреть, кто-нибудь нас видит?
Пока еще никто не подключился. Мы только зашли.
Только мы. Ага. Так, здесь будут появляться
да,
участники.
Вот, можно будет видеть. Это
хорошо.
Третья аудитория, все как обычно.
Да, хорошо, спасибо. So, well, perhaps I didn't really say anything new to you. Just what is important is this picture together with the projection. The classical notations is for the fibers. Let's call them the fibers. This way of thinking something projected to something will be universal throughout the course, and we look at the fibers. These are exactly these pre-images of the set of parameters. So this is the geometric explanation of the difference between the coefficients and unknowns. What I would like just to add, quite formally, the purely logical interpretation of the equation. That is, just let's use logic a bit. By the way, I have discussed it with the math teachers of several countries. Is it the equation with parameters? Oh no, they said. It is, because according to pedagogical theory, it is just the theory of quadratic equation, and well, what they call equations with parameters is more involved, seem more involved. But the rigorous explanation is given just in terms of logic, maybe. The question is whether there exists such an unknown where x squared plus x plus q is 0. And well, in the high school, the meaning of this question is not really precise, because, well, traditionally there can be the question whether there exists a rational root or a real root or a complex root. And I'm telling you about these matters very well known to you, just to underline the importance of fixing the domains of coefficients and variables. The main point of today's lecture will be that we should distinguish them somehow. And just to say something new, I don't know, it's a problem or just a question, and I have promised to say something that we don't know. Now in order for me to formulate it, let's fix the universal notation for the whole course. This special letter K with a special tech character will be the ground field, or sometimes ring, But the standard notation is, however, for fields. Now what I'm going to add about the arbitrary quadratic equations over arbitrary fields is just the case of the characteristic of basic ground being 2. Now let me look at the list of the participants. So there will be a small problem with the pronunciation of two names. And please raise your hands if there happen to be people here who do not understand what it means. There is no characteristic of K, yes? So you are Fukanchik Tatiana, yes, from MAI. Well, it just means that 1 plus 1 in this field is 0. We'll consider the equations over finite field. It can be the smallest finite field or the larger finite fields, but with this condition. This is exactly the meaning of characteristic. So the usual procedure of solving quadratic equation includes taking the half of the coefficient at x, yes, and extracting quadratic roots. Both operations are special in characteristic 2. So how do we solve quadratics in characteristic 2? It is not a trivial question, and well, not the one we should ignore. During the course, I'll try to explain you that whenever we are considering some polynomial equation or system of equations, we should consider it and study it over everything over which we can, including the such a bit exotic field. Now, so we still work with this equation, well, P2 is not at all trivial. I'm not saying that this case is trivial, because, well, then in such a field we don't write down minuses, since minus anything equals itself. So the condition is that the Q is itself a square. Let me use such an standard notation, explaining it just once, that it is set of squares. So we have to study, in order to understand this equation in this simplest case, we should understand what are the squares in the finite fields. Now I write again some advanced and standard answer to it. Let's work over. When Q is 0, it is really trivial. Well, we'll always use the notation. Where do I put it somewhere? The multiplicative group, K without 0, and with the operation of multiplication. Now there is a map of squaring, denoted like this. Let me write it. Sorry, how do we? Yes, this is the map of squaring. This is, let's work only with a non-zero element. Here is the set of squares. Here is 1, and here is just the kernel of please excuse me, I'm writing wrong things. Well, on the contrary, there is the square is just the half of this group. I assume, again, let me ask the people, please raise your hands, those who know the structure of the multiplicative group of the finite field. Perhaps everybody else who knows, who knows that it is cyclic. Вы, Татьяна, не знаете таких слов, да? Ну, некоторое время потерпите, скоро будет снова понятно. So, these people perhaps also understand what an exact sequence is. And now, plus minus 1 is bad notation in characteristic 2, but here we have the exact sequence of groups, yes? So I hope 5 out of 6 people here understand it. So there is some problem to describe the half of the multiplication group that is filled up with squares. So I have to find some place for the general case. As you see, it is a bit longer. This story in characteristic 2 is a bit longer than I supposed. Well, perhaps this picture is of no use at all. So now consider the case when P is non-zero. The trick is to divide the equation. So we cannot do what we are taught in school. We cannot introduce x, that is x plus p over 2, yes, to kill this term. There are no halves in characteristic 2. Instead, we should use some other trick, that is, divide the equation by p squared and, well, introduce instead x, that is x over p squared, and we'll have the equation x capital plus x plus q over p squared is the 0. So we come to a rather peculiar object, p squared, that is called Artin Schreier. Well, I'm just writing mapping because there is some exotic thing about it. It is.
The new x should be x over p.
When we divide it by p square, I think, then we'll have x small over p.
Yes.
And it is exactly x capital.
Yeah, but it's not x small over p squared. The definition of new x.
X capital. Am I wrong somehow?
У вас где замена, вот там x большое равно x малое на p квадрат, на p, наверное, просто. У вас там p квадрат.
Нет, мне надо поделить все на p квадрат.
Вы записали, вот где замена, у вас там p квадрат знаменателя, а там на p, видимо.
Sorry, thank you. Thank you, of course. Of course. So, what is tricky a bit is that it is linear. This mapping is linear, since in characteristic 2, the identity a plus b square, a square plus b square holds. So that the crazy formula would be not written on the blackboard. I stress that it is just the traditional TUAB between them annihilate. So the solvability of the quadratic equation in characteristic 2 just means well, studying some some linear Artin-Schreier map. Usually it is not injective and not surjective. So the answer, of course, the answer concerning the solvability of the quadratic is complete, but very different with the answer in characteristics different from 2. So I told you about it just to illustrate this principle. Well, usually when we are considering some equations in all the characteristics, there are some special characteristics. The corresponding primes are usually called informally bad primes or special primes, and they deserve some special study. The geometry over bad primes, soon you will understand this specific terminology. The geometry over bad primes is quite special, and this is the simplest example I can suggest. Any questions about this first example?
I have a question about this sequence exact. What happens if K is just the field with two elements?
Oh yes, you are right. Something special happens in the field of... Thank you. Yes. Or, thank you. Or 1. Of course, the square set of squares, it is just one element group, so this group has no halves. Well, and in all the other halves, in all the other cases, just half of the half of the multiplicative group is a square. Thank you very much for being so attentive. Other questions or remarks or objections?
What was the map from the multiplicative group to the group C2?
It is C2. It is just the factorization over this half. It is really
The quotient?
yes. It is just saying that the factor of sorry. Thank you. This is simple thing. Yes, it says nothing but the fact that this group is the subgroup of index 2. So we have discussed a bit the equation that is perhaps in other languages it is several thousand years old. Now I just say a few words about I keep it here, about the next non-trivial equation with one unknown. So let's move to Italy, to 16th century, and to the cubics. Let's use the same letters, just change one power. And call this equation cube also P cube. Now, what can we say about it? I see we have no time to write down the Cardano formulas. I strongly recommend everybody to refresh it. So what was I going to tell you? Well, maybe just discuss it in first discuss the problem in words. So for some centuries people were discussing whether these the cubic equations can be solved. What I'm going to discuss here for a while is to try to stress that the question is not precise. In fact, we are going today to develop the modern view on the understanding what a solution of equation means. But, well, of course, people were hunting for the solutions that would be similar to the solutions of quadratic equations. That is, formulated in terms of extracting rules. And finally, this formula was fine. Well, I'm not sure in the coefficients. The answer is, the quite formal answer is the Cardano formulas like x is, well, 1 cubic curve with some square root plus another summand like this minus square root. I recommend to everybody to, well, repeat this beautiful algebraic solution of this, but it's very difficult to understand it literally, because, well, even taking, what is the real trouble? The real trouble is that over real numbers, this formula has almost no meaning at all. But if we try to use it in complex numbers, then there are 3 cubic roots, and in fact there are something like 9 combinations of the expressions like this, and it is really tricky to extract the correct ones. But now let us try to be more precise, and let's consider the case when P and Q are rational numbers. In the Italy of 16th century, nobody would consider other examples like that, and I was going to use yes, just the notations to show different problems. So we have the sets of solutions of Q, and that is not quite trivial for the Q for which PQ the set of solutions is not non-trivial. Well, what is actually meaningful for Italians in 16th century was the question that is easy for us. So basically there are I better use the graphs, and the graph can be like this and can be like this. So this is the result of the analysis in terms of P and Q. Again, there is a phase plane, a plane PQ with a certain curve there that separates the real curve that separates the cases like this. Well, the case of complex solutions might seem trivial, but there are also details. But the main thing that I wanted to tell you about is that even here, just asking these questions, we develop, well, here, to understand it, the true mathematics developed some real analysis. And this is quite a serious question that needs Galois theory. Well, sometimes the corresponding cubic extensions are normal, sometimes no. And please raise your hands, those who understand what I'm saying now. So the question is about the Galois group of the cubic equation. Okay, so most of it, again, I'm not going to use it seriously now, just for me to understand. So from the point of view of rational numbers, there are two types of these equations with the Galois group of order 3 or of order 6. And now the final words about general polynomial solutions. Maybe I just polynomial equations in one variable. If there are no questions, I erase everything except these two equations and perhaps write down the general, perhaps I can say the general univariate equation. General, I'm just not sure, perhaps I better write it like this. So x to the n plus a1 well, and let's just spend several minutes to discuss the history of these equations. So as for the Italy in 19th century, then, well, exactly Cardano, solved, may I use the quotation marks, solved. Oh, we give the names, yes? Well, so it will be I didn't realize, thinking about this lecture, that we can become quite serious now. I mean, give it the name gen sub n. But please don't think about its coefficients as about numbers. A deeper understanding of the problem will be if our k is some other k node of what? Yes, just the polynomials. I mean, let's suppose that the coefficients are variable. I was declaring that usually it's going to be a field, so let there be a true ground field of constants, and we are working with free variables. In fact, what people knew in 19th centuries and over see that the mapping, that there are, n solutions, and the mapping n to n solutions is, so to say, 1 to n. So this is not really a mapping, but a correspondence. So such an equation has n solutions, like we are in fact trained by the cases when n was 2 or 3. So Cardano solved them, I mean, so in terms of extracting roots for n, 3 and 4. And then the mathematics stopped because mathematicians were looking for similar solutions for higher powers, and they couldn't find it, and only in 19th century it was proved rigorously by Abel and Galois that there is no solution in terms of extracting roots of this general equation. Please understand it in the same way as we can say that the equations of degree 2 and 3 have no rational solutions in numbers. This is the field of rational functions in A's, in coefficients, together with extracting roots, is something like the field of rational equations. And the general equation do not have solutions in this form. And now what I wanted to tell you, there was so theoretically I have already quoted the main theorem of algebra, and again, the main point I want to stress, discussing solutions of equations, please fix the language in which you want to get the answers. For example, for univariate polynomial solutions, you can dream about getting the answer in terms of extracting roots of rational, in terms of combination of rational functions and extracting roots, and you fail. But there is a general existence theorem that tells us that over complex numbers the solution exists. Then there is a problem, what is the expression for it? So that is the again the question of language, and now I inform you about the thing that quite possibly you don't know, that the general formula exists, the general formula for such a solution exists. It's highly transcendental and can be written down in the inversion, in terms of inversion of Barnes, sorry I'm not sure in the spelling, but perhaps it's like this, Barnes, Mellin, integral transform. So under certain numerical conditions on the coefficients, the analysis are able to distinguish some certain root of it. Well, for example, it can happen that, say, a sub n is -1 and the others are close to 0. So so the solutions will be close to the square roots, nth square roots of 1, and there is one distinguished. And for this root, you can write a highly transcendental formula. Again, it belongs to 19th century and not very well known now. Though the moral of what I'm telling you, it is rather far from the subject of our course, but it is just to stress again that the language is most important in discussing the solutions, in fact, of all kind of equations. The ones we are discussing, as well as differential equations, functional equations, and so on. Any questions about what I've told you up to now? Again, this is just a preliminary discussion. Everything will be discussed completely. Now, sorry, there is something controversial on the desk, on the blackboard, because our title is Indefinite Equations, but what we have discussed up to now did not belong to the theory of indefinite equations, and well, the classical notion of it was that the number of unknowns exceeds strictly the number of equations. Well, of course, the system of equations is meant, but up to now we have discussed only the situation of one equation. But still keep with one equations for some time, perhaps for the end of today's lecture. And let's consider now some indefinite equations, again paying special attention to the names of equations. In fact, there are no strict rules according to which we should use only last letters of the alphabet for the equations. Here I hope I'll be able to draw something and you will believe that I'm drawing the cone, the straight cone with these axes A, B, C. The choice of the letter, of course, is motivated by the Pythagorean triangle. So in some sense, every point of this cone is, or not every, but maybe of 1/8 part of it where all the coordinates are positive. Every point is a triangle. And starting from very old times, people were interested in the integral solutions of it, that is, in the integral points. For instance, knowing this point, sometimes called the Egyptian triangle. So the cone is defined by a homogeneous equation. So there are certain non-interesting solutions like 30, 40, 50. We don't consider them. The primitive solutions are those for which the coordinates are coprime. Then there are some non-trivial ones like 5, 12, 13, and so on. And maybe what I'm quoting is the first result in the whole mathematics, because now let's ask the question we are discussing, the set of solutions over Z. Yes, and let's put mark that we are interested in the primitives one, and the set turned out to be infinity. And in some sense, this fact is perhaps about 4,000 years old. As we know from the first document, mathematical document available, I think it's called like this, 322 or something like that. Anybody can Google it easily. So a few words about this document. This is just a clay table, глинобитная такая штучка, with about 15 this Pythagorean triples. So the solutions of these equations. The largest of them are really enormous, so we can be sure that the ancient Babylonians, about 4,000 years ago, working about 4,000 years ago, had some general methods of finding the solutions of this equation. Now we can do something more geometrical to it. The modern understanding of it is, well, I'm not asking you, perhaps everybody knows what I'm going to tell you in the coming 5 minutes, but I just want to stress the concept somehow. So, introducing the new variables like A over C and B over C, we turn to the standard circle. And here the geometry is very clear, but I want to emphasize here that what we are doing, we are looking for rational solutions of it. So the rational solutions, we have a perfect definition of this set as soon as we have the name of the equation. So it sits in the circle of R, and what we really draw here, this is and this is the circle of R. This is what we call the circle. As for the rational points here, it is not quite obvious that this set is infinite, and we'll work with lots of other plane curves for which the rational points are the set of rational points are finite or empty sometimes. Here we know some exotics like the triple and how do we know that the set is 0? We know it using the new concept of solution of indefinite equation, solution. In the most optimistic situation, the solution is the maybe. It is the rational parameterization. For the time being, I'll just give an example. There are the formulas. Well, read by here. Sorry, there are lots of books in which you find what I'm telling you about. I don't know why the authors put this special point in the lowest part of the circle. I think it is important to put it where I have put it. Here is the general line of the set of lines through the leftmost point, and I use this one because, well, the answer is, the parameterization is like this. I'll write it down and give a couple of questions about it. T squared y is 2t t square. So in some sense, this is the solution of this indefinite equation. Now please raise your hands, those who recognize these formulas. Now please tell me, you know it from introductory courses of algebraic geometry or from the high school?
Both.
Both, okay. So what is really important that t, the good meaning, the good geometrical meaning is when t is tan of phi half and well x is cosine phi and y is sine phi. So here is the phi. So, well, what I wanted to show you that thinking geometrically, we use such objects. But what we look at is this set here or this set here. That's right. Also, here we are interested in the integer solution, and it also belongs to z cube sitting in r cube. And the words, the geometric words, circle and cone are about the real sets of solutions of equations. And well, our geometric intuition is trained to consider the real sets of solution, but it is by no means the most efficient way to understand them. So, any questions about this? No, perhaps let me write down something that does not exactly follow, but perhaps this formula also is one of the, is rewriting that one, but not completely, because there is if the triangle is Pythagorean, well, there is the even leg of the triangle's leg cutted leg and the odd leg, and well, we have made some choice. So this is the solution up to renaming A and B. So one could hope to get this kind of solutions for more general system of equations. But now I give some, well, objection or ruin this hope. I write it. If there are no questions about that, I just leave this question. Any questions about what is on the blackboard now? Okay, I erase everything. It was just example, and tell you something that can be interpreted as bad news. Bad news. So, this is some happy cases when such parameterization exists, but usually sets, or perhaps since I'm writing something professional, the varieties. So here I assume some knowledge of algebraic geometry and use the terminology from the most elementary part of it, when the algebraic variety is just the set of solutions of polynomial equations. Varieties are not rational. By definition, it means that such a parameterization is impossible. Now please raise your hand those who know what is a rational algebraic variety. And so can I conclude that no, I'm unable. Who? You please pronounce your name.
一绝
E.G.
yes.
E.G. Have you taken any course of algebraic geometry in your life?
Yes.
Oh, then perhaps you were told about the varieties being rational or irrational. So perhaps it is some misunderstanding that you didn't raise your hand. And
Yes.
Have you taken any course in algebraic geometry?
Yeah.
Then you also know what is a rational variety. The field of rational functions on it should be isomorphic to a purely transcendental extension of the field of constants. Well, we'll fix what we are going to use. So this is just some extremity. However, they do not reduce to the quadratic equations that the rationality of the corresponding varieties we were using up to now. And let me give you another example. So turn to, cubic surfaces, the example from cubic surfaces. Let's consider, I think it's a good practice to start discussion of arithmetic geometric problems with some numerical facts. So you can check this beautiful equality. So this is a puzzling fact. psychologically, I would say that if we like the equalities like this, then we have the inherent interest in arithmetic geometry. And then it is natural to ask about the others. Well, to turn it to other solutions. Now we have the procedure is a bit inverse to the usual one. Originally, people are given an equation, and are supposed to look for solutions. Here we are given a beautiful solution of what kind of equation? Let's give it the standard name, Fermat 3. Fermat 3, the equation is like this. We just take it more geometrical, more symmetrical in variables, so as to write x3, y4, z5, and w negative 6. W negative 6. So this is another. So, you could think that I have written the equation in the 4 space, so that this is a 3-dimensional object. And I have to ask to raise your hands those who understand the words projective varieties. Yes, do you? Well, then you should imagine that in fact we can move to the 4-dimensional space, but since the equation is homogeneous, it is also a cone. It consists, as well as the true 2-dimensional cone, it consists of the lines. Therefore, basically, it defines a surface. And I've mentioned this one for 2 reasons. Perhaps I just, to relax, I give a historic anecdote. So maybe the true story was like this. The great British mathematician Hardy in 30s visited Ramanujan and just looked at some taxi number. I don't remember it. Let me just draw it. So there was some number N, and Hardy said, nothing special. It is a number not distinguished but any property. Ramanujan was sick in the hospital and answered, not at all. N is the smallest natural number such that n is represented in terms of sums of two cubes in two different ways. So, how do we call it? Perhaps, sorry, you are Alexander Yurievich? No, I didn't cannot get you. I'm going to use notations that will be clear to those who are in good terms with projective geometry. So that is the surface Fermat 3 contains, as we know, 2 points. I'm going to write the homogeneous coordinate, of this is what I emphasize, that it contains 3, 4, 5, 3 column 4, 5 minus 6, and then Ramanujan's x1, say y1, negative x2, negative y2. So this is a non-trivial fact. The standard question about arithmetic geometry is whether the set of solution is infinite. Here it is, and I claim that the set of solutions of that is infinite, and very briefly explain why it is so. It is just because the cubic surfaces, perhaps people with some background in algebraic geometry know it without my reminding, but it's not really difficult to draw the picture. Surfaces are rational, and the argument is quite easy. Basically, there are 27 lines on them, but it is sufficient to choose 2 skew lines, and here is a rational parameterization. So there is a line in space that intersects the cubic surface in one point and in another point, but basically so if we have u here and u coordinate here and v coordinate here, then we have the third point, the third intersection of this broken line with a cubic surface, and it is a rational function in uv. I don't remember the details about Ramanujan story, but I think it is a good exercise to fill in the details. So this is about a half of what I was going to say today. I don't know why it turns out to be much slower. Then I'll try to speed up. Perhaps you know the program. Well, and we have to stop now. The time is not shown here, but I see my watch. So usually our lectures are from hour 30 minutes to hour 40 minutes long. And now I stop first to ask all of you about questions, remarks, or suggestions for the future. Well, maybe I briefly tell you about what I was going to tell you today. The next part. So this one that is written is called indefinite equations. Then I wanted to discuss what is algebraic geometry, in fact. So we wanted to discuss three answers. The first one is with what we worked a bit today, that is algebraic geometry studies the sets of solutions of polynomial equations. And there are two other answers. I'll just pronounce them. They will be explained in the following lectures. There are 3 points of view. In fact, we have covered 1.5. So the second point of view about algebraic geometry is close to the first one, though is formulated in much more advanced terms. It is the study of such sets, as I said, over all the fields or rings of algebras in the world. In the modern language, it means that every system of equations, and this is why I am so touchy about giving them names, just define a functor from the rings, in the simplest case, from the rings to sets. It is quite a special functor. May I ask you now, please raise your hands, those who understand the word functor. Oh, very good, very good. So, it is called the functor of points, and this is what we are going to discuss. And the third point of view is somewhat more general, and we really need it for our consideration. It is the sort of modern language of algebraic geometry, that is the language of Grothendieck schemes. And again, let me ask you, please raise your hands, those who know something about Grothendieck schemes, that is, have some idea of abstract algebraic geometry. basically two hands, yes? So, I don't know at which level of detailization we'll try to discuss it. Mostly I will give just brief definitions and then return to this point of view only when we really need it in studying our some algebraic equations that are really related to our subject, arithmetic surfaces. So then, thank you for your attention, and excuse me, there is one thing I have forgotten, and one declaration more. Please write down your emails. Those who are going to participate in this course, please write down your email. Nobody else joined us. And I should declare that the next lecture will be missed. We meet in 2 weeks, no, not in 1. I'm going to the conference and I have no idea what. In Armenia, I'm not at all sure that the distant tools will work. And as you see, even here, they are tricky. So we meet in 14 days. Okay then, thank you for your attention.